Alright, so what we learned so far has been called classical physics, and this physics was all figured out before the year 1900. All the physics figured out after the year 1900 is called modern physics, and that's what we're learning about right now. End of the 1800s, physicists were feeling very arrogant about all the different things they figured out, especially about their understanding of light. It was one thing that physicists were very confident about, and that was that light was made up as if it was made up of waves. For example, if you shine light from one medium into another medium, it bends like this. What is this property of waves called? Refraction. Yeah, this is refraction. All waves refract, and when the light refracted, this was conclusive evidence that light behaves as if it's made up of waves. What's this, like when a crest and a trough move in and share the same space at the same time? Interference. And basically, it's destructive shown here, and when the two waves meet and share the same space, if it's a 5 amplitude and a -3, then just for a moment you'll have a little amplitude of 2. And then a moment later, you'll have your 3 continuing on its way, and your 5 continuing on its way. Yeah. We saw conclusively that light does this sort of thing. Light can cancel itself out. Only waves cancel themselves out. All waves do this sort of thing when going through a barrier. What is this one called, Tommy? Diffraction. When light was shined through a little opening, it did this sort of thing. Again, conclusive evidence that light was made up of waves. But this is the experiment that rocked the physicist's world, the photoelectric effect. It was the first experiment that showed that light behaves as if it's made up of particles. Einstein was the one who could think outside the box, and he looked at the results of the photoelectric effect, and when he first made his statement that the light is behaving as if it's made up of particles, all the other physicists were like, what are you talking about? That's one thing we already know for sure. Light is made up of waves. And Einstein said, I'm not saying, it's not behaving like a wave in all those other experiments, but in this experiment, it's behaving as if it's made up of particles. So basically, what is the photoelectric effect? Well, if you shine certain light on certain metals, the light will actually kick some of the electrons off the surface of the metal out into the air. That whole process of light kicking electrons off the metal is called the photoelectric effect. And these ejected electrons are called photoelectrons. By studying the results of this experiment, it was shown that the light in this experiment was not behaving like a wave. It was behaving as if it was made up of particles. So now we take a closer look at the actual apparatus used. And inside a glass tube that has all the air sucked out of it, so it's called a vacuum tube, there were two metal plates, kind of like a capacitor, with a lot of space in between. Light was shined through the glass plate onto the metal plate that was charged negatively by a variable voltage source. By turning the dial, you could change the voltage. Over here was the negative terminal. Over here was the positive terminal. And basically, when the light shined on the plate on the left, the electrons were ejected, and then they were attracted to the positive plate, thus completing the circuit. So electrons could move through the wire up to the plate, then be ejected off the plate, cross over to the positive, and then cross down to complete the circuit. There were two things that were measured. One, how many of these photoelectrons were ejected each second? Does anyone remember how that was determined? Do you remember, Dave?
Calculate the speed of the fastest.
No, you're getting ahead. How was the number of photoelectrons ejected?
Ammeter?
By the ammeter. By putting an ammeter right in here, you could determine the number of photoelectrons ejected. Then, the second thing that was measured was the kinetic energy of the fastest of these photoelectrons. Does anyone remember how that was determined? Dylan?
Increase the voltage until no electrons can get across enough to stop the voltage.
Correct, but what do you have to do first before you increase the voltage?
So you have to find the point at which only one electron can go by.
Yeah, but you're forgetting one crucial step. Because the way it's set up now, that plate on the right is positive, and the plate on the left is negative. And I didn't have you guys redraw it.
You have to switch the polarizations so that the negative one becomes positive and the positive one becomes negative.
Exactly. Switch the terminals of the voltage source, crank up the voltage source until the plates finally stop the fastest of the photoelectrons, and you get the stopping voltage. So, two things measured. The number of photoelectrons ejected, that was measured by reading the ammeter. The ammeter read the current going through that wire, which is known as the photoelectric current. If the current in that wire on the right was, what did we use as our current yesterday?
0.05.
0.005 amps. Then we know that that is equal to 0.005 coulombs per second. And then if I convert the units, I know that 1 coulomb is equal to 6.25 times 10 to the 18th elementary charges. And what did that come out to? Oh, we said 3.125 times 10 to the 60 electrons per second. So by knowing the current going through that ammeter, we could determine the number of electrons ejected off the plate per second. If the current was 0.005 amperes, then the number of photoelectrons ejected would be 3.125 times 10 to the 16th electrons per second. The kinetic energy of the fastest electrons ejected, by switching the terminals of voltage source increasing the voltage until feistiest. How do you spell feisty? Feist, like that?
No, F-I-E-S.
The feistiest, increasing the voltage until the feistiest photoelectron was ejected.
Switch the ion.
Switch the what?
Ion.
At the beginning?
Yeah. You know my arm. You don't have to do that. We'll get it this time tomorrow. Alright, so US basically
Okay, welcome back. So, here we have light shining down on the negatively charged plate. Electrons are being ejected off the plate. They're going across to the right. We can figure out how many of those photoelectrons there are by the ammeter here. But we want to figure out how much kinetic energy the fastest of those photoelectrons has. So, here's what we do. We switch the terminals of the battery.
Hey!
And when we switch the terminals of the battery, right, those electrons that are heading over to the right to that positive plate, they're like, what's going on? Because nearly instantly, this plate over here becomes negatively charged. And the plate over here becomes positively charged. So most of those ejected photoelectrons, they're just like, and end up going straight on back. Okay? But some of the more feisty photoelectrons that have a lot of kinetic energy, because the light kicked them off with so much oomph, they keep on going across. So there's still a little tiny baby reading in the ammeter here. So this got the physicists mad. So they said, you feisty photoelectrons, I'll teach you. And they cranked up the voltage source, and that made this thing even more negative, and this even more positive. And the number of photoelectrons going across dwindled down even more, and the ammeter reading became even less. And this process was done, the voltage was increased, until finally all the photoelectrons were stopped. And we know that happened because, well, how do we know that happened? The ammeter finally read 0. And that voltage that the voltmeter over here, that the variable voltage source, gave us, that's called the stopping voltage. And let's say, for example, that the stopping voltage was 150,000 volts. By knowing the stopping voltage, we could figure out how much kinetic energy the feistiest of those photoelectrons, had. So let's take a look at that calculation. V stopping equals 150,000 volts. And we want to know the kinetic energy maximum, the maximum kinetic energy of the photoelectrons. Well, recall that voltage is just like work, but it's not the whole work, it's the work done per charge. So basically, if we rearrange this, we know that the work done to stop those feisty photoelectrons equals the voltage times the amount of charge each one of those little particles had. So if the stopping voltage was 150,000 volts, and since we're dealing with electrons, the charge of the electron is negative 1.6 times 10 to the negative 19th coulombs, we could figure out how much work was done to stop those photoelectrons. And the work is negative because the electrons were going to the right, but the force slowing them down was acting to the left. Could someone crunch that out for me? How much work would it take? Not really. You don't have to. What you got, Reed?
2.4 times negative 14.
Joules. So, basically, the work is negative because, again, it was used to stop the photoelectron. Don't get bogged down by the negative. I'm just going to actually just drop it there, because if it took 2.4 times 10 to the negative 14 joules of work to stop those feisty photoelectrons, guess how much kinetic energy the feistiest of those fast photoelectrons had? Yeah, not much. If a car has 1,000 joules of kinetic energy, how much work does it take to stop that car? 1,000 joules. So if you know how much work it takes to stop something, you know how much kinetic energy it had. So basically, therefore, we know the kinetic energy of the fastest, the maximum, photoelectron equals 2.4 times 10 to the negative 14th joules. So once you know the stopping voltage, you could calculate the maximum kinetic energy of the ejected photoelectrons, or the ejected electrons. So now we're ready to talk about the results of the experiment. As with most scientific experiments, you go in with a hypothesis. You go in with an idea of how you think things are going to happen. So basically, here is what wave theory predicted. Wave theory suggests that light is made up of waves. And basically, the bigger these waves are, the bigger their amplitude, the more energy these waves have. Just like if you're jumping waves at Jones Beach, and you jump another, like a 4-foot wave, and then a little 5-foot wave, and then if you look and there's like a 12-foot wave coming at you, you know you're in trouble, because that bigger wave has more energy, it has the ability to mesh you up more and do work on you and pound you into the sand. So basically, we know that light waves, the same thing applies, and the amplitude indicates the energy of the wave. And light waves that have a bigger amplitude, they appear brighter. The brighter the light, the bigger the amplitude of the light waves. So basically, amplitude corresponds to brightness when it comes to light waves. And a fancy-dancy way of saying brightness, the intensity of the waves. That's intense. So, wave theory predictions. If you increase the intensity of the waves, the number of photoelectrons ejected will go up. If you're splashing that piece of metal with brighter light waves, it's like they're bigger waves, then you would expect more photoelectrons to be washed off the metal. So the brighter the light, the more photoelectrons should be ejected. The other wave theory prediction, the brighter the light, I'm drawing an I down here for intensity. This is intensity, the brightness. The Ke max of the photoelectrons well, again, if you use brighter light, bigger waves that have more energy, then you would expect that when the electrons are ejected off the metal, they would have more energy themselves. So again, wave theory predicted direct relationship. Now, obviously we know that the photoelectric effect turned out not to support the fact that light is made up of waves. So both of these hypotheses were not correct. It turns out that the one on the left, this turned out to be true. If you shine brighter light on that metal, you do get more photoelectrons ejected off that metal. But the one on the right, yes?
Stays constant.
Stays constant, yes. The one on the right, if you shine brighter light on those that piece of metal, the electrons aren't ejected with more and more kinetic energy. So this turned out to be false.
Really, it should just be like a flat line.
Yeah, and we're going to draw that next. it turned out it didn't matter if you used really, really dim light or if you used really, really bright light. The electrons ejected off the metal plate had the same maximum kinetic energy. Again, at first they thought it was, a technical glitch. Something must be not connected correctly. But when it was done over and over and over and over again, basically, no matter how bright this light was, the maximum kinetic energy of that feistiest photoelectron stayed constant. The first point was true, though. If you use brighter light, you do get more photoelectrons. It was the second one that was false. The brighter the light, same amount of kinetic energy. So, what's the next logical question? If the brightness of the light didn't affect the maximum kinetic energy, what do you think the scientists asked next? Dylan? Exactly. You're thinking like a scientist. What does affect the maximum kinetic energy of those photoelectrons? Not the brightness, but no. It's a quality, it's a characteristics of the light. What are we going to change about the light? The brightness of the light didn't affect it. The color, the wavelength, what were you going to say, Alex? The frequency, that's all the same answer, really, because if you have a different color, it has a different wavelength, it has a different frequency. So basically, all three answers are correct. The color, the frequency, or the wavelength. Most times, scientists would the common answer is the frequency of the light. But with the understanding, if you have a different frequency, well, that's a different wavelength. And if you have a different wavelength, and a different frequency, that's also a different color. So basically, the frequency of the incoming light. So this is a good point to take a stretch. So here's what the results look like. If we make a graph, and down here we put the frequency of the light that's being shined down on the metal. What are the units for frequency? Do you remember? Hurts so good. So the frequency of the the incoming light being shined on the metal, and over here we have the kinetic energy of the fastest ejected electrons. And at first, a low frequency light was used. What is the lowest frequency light that's in the visible range? You remember, Peter? Red. Okay. Red is a low frequency light. Violet is a high frequency light. Right. So when red light was shined on that metal plate, nothing happened. even if they cranked it up and like put it really bright red, no photoelectrons were ejected. So we can't even put a point on the graph because basically, when this frequency down here was used, nothing happened. No photoelectrons.
Something's supposed to happen.
Exactly. And nothing happened. And then, when a little bit higher frequency light was used, say for example like what? Orange. Aren't you glad I didn't say banana? Yes. If you use orange, again, even if the light was super bright orange, no photoelectrons at all were ejected. What? This light is bright. I mean, you can put sunglasses on. Nothing. Finally, when a little bit higher frequency light was used, like mellow yellow, yes, the electrons were ejected. But they didn't have much oomph to them. As a matter of fact, they didn't have hardly any kinetic energy at all. They were ejected, but not with any kinetic energy. So basically, we get our first point right here at this frequency right here. This is the first frequency that finally got the electrons ejected off the metal plate. There's a name for this first frequency that gets the electrons to finally start jumping. It's called the threshold frequency. And its symbol is an F sub O. Because it's like the original frequency that gets the job done. The threshold frequency. I'm going to put that on another page here. F sub O. Threshold. I think there's two H's. Threshold frequency. Double check me on that. There's only one H? Like I said, don't make this mistake. There's only one H. Threshold frequency. It's the lowest frequency that you could use to get the electrons ejected off the plate. Now remember, we were on a quest to figure out what affects the maximum kinetic energy of the ejected photoelectrons there, yes? So if you up the ante now, and you go up to a higher frequency over here, then not only were the electrons ejected, but guess what else changed? How much kinetic energy they had. So now, basically, if you use this next higher, you would get a higher, maximum kinetic energy. So basically, if you use a higher frequency over here, not only were they ejected, but they were ejected with this much kinetic energy. And then if you increase the frequency even more, they were ejected, but they were ejected with even more kinetic energy. And it actually made a direct relationship. Once the threshold frequency was reached, if you increased the frequency, there was an increase in the maximum kinetic energy of the ejected electrons. It depends on what metal was being used. Okay? And that's going to come up in a moment. Matter of fact, why don't we talk about that right now? Okay? I'm going to put a duplicate screen in here. Let's see here. Okay. Now, it turns out that if you go back to the apparatus, everybody okay? Okay, Dorothy? If you change this metal, maybe the original piece of metal was zinc, and maybe now you're going to use a piece of copper, yes? If you change this piece of metal right here, well, then there would be a different threshold frequency. So basically, now with a new piece of metal over here, if you go and graph the result on that same graph as before, basically, this one here we could call, metal A. And then now if we do metal B in green, maybe its threshold frequency was like right here. And this is the threshold frequency for the second metal. But interesting enough, once the threshold frequency was met, the increase in the kinetic energy by increasing the frequency went up at the same rate. So this would be the data line, collected for a second metal, say metal B. And then if you had a third metal, like this one right here, it might have its own threshold frequency, but once again, the increase would have the same exact rate as the first two. So every metal had its own threshold frequency, but what graphical characteristic did all three of them have here? The slope. And that's what Einstein focused in on when he tried to figure out what was going on here. So basically, it turns out that the slope of this graph is a really important constant. It's named after a different physicist who did a lot of experiments with these black boxes where white light was shined into a box, and the white light just kept on reflecting on the inside of the box, and the temperature of the box would go up. It's called black box radiation. And the scientist who did all this work, his name was Max Planck. Yes? And basically, the slope of this graph is named after him. So they all have the same slope. Slope is called okay, again, use your iPhones to help me out here. Planck, what is there a C in there or just a K?
There's a C.
I think with his name there is a C. Slope is called Planck's constant. Oh, that's what I was going to look up, so you have it for me. Slope. The symbol used to represent Planck's constant is an H, and H turned out to be equal to 6.63 times 10 to the negative 34th. Okay, but I'm going to just first start off with the units from the graph. What you see is what you get. So what would be the units of the slope? Rise over run? This over here? That's what I'm talking about, people. Joules over Hertz. Now, from that formula, period equals 1 over frequency. Period is measured in seconds. Frequency is measured in hertz. So, another way of saying 1 over hertz is to say seconds. Yes? So, a second is equal to 1 over a hertz. Yes? So, basically, sometimes you'll see Planck's constant written as 6.63 times 10 to the negative 34th joule seconds. Okie dokie. So, Einstein took a closer look at this slope because he said there's something interesting going on here. No matter what type of metal you use, even though the threshold frequencies were different, each metal showed a graph that had the same exact slope. Now, basically, anytime you calculate slope, you need 2 points. So basically, one point that we can analyze is this one right here, where the threshold frequency is used. And if the threshold frequency was used, how much kinetic energy did those photoelectrons have? 0 joules. And then a second point could be used up here, yes? And with that second point up here, that corresponds to some higher frequency light. And when you use that higher frequency light, the photoelectrons were ejected with some higher amount of kinetic energy. So, this is the kinetic energy maximum that corresponds to the higher frequency light used at this second point right here. So basically what we're going to do is use these 2 points to calculate the slope of the line. So here we go. Slope equals delta y over delta x, or some people say rise over run. So the slope is going to be equal to your delta y. Well, what's delta y? 0. Some higher kinetic energy associated with the higher frequency light. So when I go to do your delta y here, it's going to be the subtraction of these two values over here. So basically what do you have over here? The Ke max of the photoelectrons when the higher frequency light was used minus what? 0. And then those same 2 points, the delta x, here and here, well, it's going to be the higher frequency light used minus the threshold frequency over here. So your delta x is going to be the higher frequency light minus the threshold frequency. And of course the slope was equal to Planck's constant h. So H turned out to be equal to the Ke max of the photoelectrons all over the difference in those two frequencies. Now this formula is just going to be rearranged. I'm just going to like cross multiply and distribute the H. And when I do that, I get this formula here. The kinetic energy maximum of the fastest ejected photoelectrons equals H times F minus H times FO. I just crisscross multiply, distribute the H. And this is Einstein's famous photoelectric equation. And what we're going to have to do first thing tomorrow is discuss, what the heck does this mean? Because at first glance, it just seems like the slope formula rearranged, but it turns out that there's a very simple, basic explanation for each of these terms. So we'll pause with this question. What does this all mean?